Hi, my name is Zev Kurtzman. Today we'll be discussing the mechanisms for controlling slow-wave sleep. So the goal of this lesson will be to understand the mechanisms involved in controlling stages 3 and 4 of sleep, otherwise known as slow-wave sleep. And the main thing to understand with all these EEG readings is essentially that wakefulness is characterized by mainly desynchronous brain activity, where beta is more desynchronous than alpha, but both are desynchronous wave activities. And when you're drowsy, your brain activity starts to become more synchronous. And as you enter deeper levels of sleep, your brain activity becomes more and more and more synchronous, which is correlated with less mental activity. So this is because all the neurons are firing in a synchronous manner. They're not firing at different times, doing different tasks. They're all firing at the same time in a regular type of way. So that's the main thing to understand about what really characterizes sleep versus wakefulness. And the interesting thing is REM sleep, where you're most likely to dream, is actually quite similar to brain activity in wakefulness, except with a few physiological changes that make you actually sleep and not move around. But that's a different topic. So like we said, stage 1, there's the presence of theta waves, so more synchronous brain activity. This is the transition between wakefulness and sleep after just being drowsy. And then there's stage 2, which is also more theta waves, as well as some sleep spindles and K complexes. So a sleep spindle is just a short burst of waves, 12 to 14 hertz. And then K complexes are the forerunner to the next slowest wave, which are delta waves, and these are less than 3.5 hertz. And stages 3 and 4 are really mainly on a continuum, where stages 3 is just less delta waves and stages 4 is more delta waves, so more synchronous brain activity. Here is a physiological description of or characteristics during REM and slow wave sleep. So in order to understand sleep, you have to understand really what being awake is. And to understand that, there's 5 main systems involved in arousal. There's the acetylcholinergic system, which is associated with cortical activation. There's the neuroadrenergic system, which is associated with vigilance. The serotonergic system, which acts in the activation of autonomic behaviors. The histaminergic system, which is there for maintaining, associated with maintaining wakefulness, and orexinergic, which is associated with actually exciting these regions. So the fact that we need to sleep when it might otherwise be advantageous to not sleep indicates that the need to sleep is caused by the buildup of something, and it turns out that the buildup of this is actually adenosine. And so this actually makes sense because adenosine is released by astrocytes around cells which are metabolically active. So astrocytes contain glycogen, which can be used as fuel for neurons, and low levels of glycogen produce extracellular levels of adenosine. So when neurons are metabolically active, they burn a lot of fuel. They take glycogen from the astrocytes, and this decrease in glycogen leads to a buildup of adenosine. And adenosine builds up during wakefulness and decreases during sleep. So there's 3 factors of sleep control. There's homeostatic, which we actually just talked about. This is the need for metabolically active neurons to rest and refuel, which leads to the release of adenosine. And then there's allostatic, which acts to override homeostatic control. And this is the orexinergic system, as well as the circadian system, which is mediated by the time of day and factors of light. So the sleep-awake system is actually an on-off switch, and this is because it's mediated by 2 areas of the brain which inhibit each other. So both cannot be on at the same time. So how this works is that sleep neurons are located mainly in the ventrolateral preoptic area, the VLPO, and they are excited by the buildup of adenosine. This is where adenosine comes in. So neurons from the VLPO secrete inhibitory GABA and is connected to the 5 areas associated with wakefulness. And then it also receives inhibitory inputs, like I said, from these areas, including the histaminergic, the serotonergic, and the neuroadrenergic systems. And the activation of VLPO leads to inhibition of these areas, while activation of these areas lead to the inhibition of VLPO. So, like I said, on-off switch. It's turning a light on or off. And then there's allostatic control, which works to excite the wakefulness promoted areas of the brain, and which leads to inhibition of the sleep promoting region of the brain. Orexinergic neurons form connections to almost every part of the brain, and all of the connections to the wakefulness areas are excitatory. So it acts to hold the on switch on. So what affects orexinergic neurons? So the biological clock sends excitatory signals to orexinergic neurons during wakeful hours. Hunger excites orexinergic neurons, whereas satiety inhibits them. And then the VLPO actually also sends inhibitory signals to orexinergic neurons to enable sleep to overcome other signals, which is just kind of funny because it just means that sleep will always have the final word. Eventually you will have to go to sleep, and it's actually built into your system that you will have to sleep eventually. So final picture. So prolonged wakefulness leads to the buildup of adenosine, which acts on the VLPO. This inhibits the wakeful regions of the brain. This wakeful region of the brain also inhibits VLPO. And then the orexinergic neurons act to excite that arousal system, but are also inhibited by VLPO. And then the orexinergic neurons are excited by these following factors. And then the interesting thing that I found was that we always associate REM sleep with dreaming, and people think that REM is the only time that you can sleep. But researchers actually found out that dreaming can occur in non-REM sleep. So researchers gave subjects the antidepressant clomipramine, which actually suppresses REM sleep. And they found out that these subjects, it was a double-blind placebo study, and they found that even subjects who didn't have REM sleep were still able to have dreams, and they reported them with similar qualities of people who are woken up during quote-unquote REM sleep. So this shows that REM sleep is not just the only time when you can dream. You can dream in other stages of sleep, apparently. And here are the works cited. All right, thank you.